Hello, everybody. This is Miss Peachy from your WCA Physics A class. We are looking at Unit 6, Lesson 6, which is on simple machines and efficiency. And some of this is going to seem pretty basic to you guys, but we do work, there's always a little bit more than you've already learned in the past in here. So our keywords are conservation of energy, that just keeps coming back again and again, doesn't it? Efficiency, useful energy, and waste energy, at least in the first part of the lesson. So I was talking about energy and how when you use energy, not all of the energy is necessarily used to do something useful. So according to the law of conservation of energy, energy cannot be created or destroyed, right? But it changes from one form to another. So energy input should be equal to energy output, but that doesn't mean that the energy output is the same form as the energy that's being put in. So some energy is quote unquote wasted in things such as heat, motion, and we often talk about heat as probably being the number one factor. So think about friction, for example, which produces heat and is a part of a lot of machines. It's really pretty impossible to get rid of friction. So we can calculate what's known as the efficiency of the machine, and efficiency is energy out divided by energy in times 100%. Um, and typically, you kind of leave this out, multiply by 100, it should give you the percent efficiency, okay, rather than 100%. All right, so the formula is used to figure out useful energy, the energy that is being used like to make heat is considered waste energy. And it talks about how certain things have different types of efficiency. For example, solar panels have an efficiency of around 15%, meaning only 15% of the energy coming in is being used to do useful work, and the remaining 85% is somehow lost, oftentimes as reflected heat or light or something like that, but isn't being used for what it's intended for. Looking at other types of systems, electrical vehicles convert about 77% of the electrical energy taken from the grid into the wheels. So that's much more efficient. Whereas a gasoline powered engine, conventional gasoline powered engines are closer to 15 to 30%. We also look at types of light bulbs. Now, there's two in here. There should probably be a third light bulb. We have a conventional incandescent light bulb where there's a tungsten filament that needs to get hot and it glows. And then we have a compact fluorescent light bulb, which contains gas, and that gas inside is excited, and the electrons are moved to higher orbitals. And as they fall back down to where they're supposed to be, the excess energy is released as light. But most of us probably are using compact fluorescent, or not compact fluorescent, but um, what is it called? Oh my gosh, you guys, I totally lost what it was called. LED light bulbs these days, which are even more energy efficient, right? And it also talks about how your standard oven is less efficient than convection ovens. So it's giving you some problems. I think the equations for efficiency are easy enough that I don't really need to go through that with you, but if you have questions, let me know. And then we have another section, and our keywords here are conservation of energy, displacement, efficiency, energy, friction force, mechanical advantage, simple machine, and work. And we've learned about simple machines probably going back to like first grade. Simple machines are things that take and make work a little easier. They don't reduce the amount of work, but they oftentimes reduce the amount of force that you need to apply, or they act to multiply your force, or they act to decrease the distance. But most of the time, we talk about an increase in the amount of force that's being used. So we have to realize that force times distance, so work is equal to, that's supposed to say work. Okay, let's try that again. WORK is equal to force times distance. You may have seen this before in physical science as well. That is the force that is applied in the direction of motion. So if I'm pushing a box along a floor, I'm pushing it with a force over a specific distance. I'm doing work on that box. Work is done when force is applied, right? But also that work and energy are kind of interchangeable, whereas energy can be both kinetic and potential. Work is only in motion. You have to be moving something. And they have the same units of measure. You're still measuring with joules. So work or energy kind of mean the same thing in this particular situation. So work in is equal to work out. So if you're putting work into something, you should get the work out of it. So we have to break that down into force times distance in equals force times distance out. So a simple machine, what it does is it allows this force here to be little, making that a lowercase just so we can understand, and this distance to be real big. And then what happens is this force ends up being bigger, but the distance is real small. So in other words, I don't have to push so hard, but I may have to push it further. And then the object that I am trying to move, I'm able to apply a greater force to it, but it's not going to move as far as I want it to move. Okay? Or as far as it could move otherwise. So an example here is, oops, I'm going to get back to that in a moment. I want to look at an example, and we'll go down to mechanical advantage. Nope, I missed where I was supposed to be. I'm trying to find. Okay. Give me 1 second. I thought that was a picture of a ramp on here somewhere. But oh, here it is. So let's say I need to get this box into, let's say there's a truck with a really high like door in the truck, right? So there's the door for the truck, and it's got these, I don't know, wow, it's not a very good drawer. These are the wheels, right, of the truck, but that's the door. And I got to get this box into it. I could pick the box up from the ground here. Sorry, and I could move it directly into the truck, right? So I could do that. I'm just gonna erase my my one line here, okay? But I can move it directly into the truck here, just like that. So the distance that I'm removing that would be a fairly short distance, just the height from the ground to the truck. That's it. But it's really heavy, and I can't lift it, and it's just too heavy for me. So otherwise, I can use a simple machine. I can use this ramp, and I can move it a longer distance. So if you look, L here is much greater of a distance than H. Therefore, because I'm moving it a longer distance, I apply less force, right? So my force is less, but my distance is bigger. That's what I'm pushing with. We call that the input. That's your input work, or input force and input distance. And the height, I'm actually raising at that height. So I'm able to lift a very heavy object a small distance. Does that make sense? So just going back a little bit here. That's what simple machines do, right? So what we say is that this gives us mechanical advantage. The force out divided by the force in is what's known as mechanical advantage. Say I'm pushing with a force of, I'm going to use imperial units just to make them easier, but say that I can lift like 30 pounds. That's it, 30 pounds. I'm pretty weak, okay? So all I can lift is 30 pounds, but by using that ramp, let's see if we have that down below. No, by using a ramp that is 3 foot long and 1 foot high, I can actually lift 90 pounds. So 30 divided by 90 is 3. So basically that ramp allows me to lift 3 times more than I could otherwise lift. And that's what mechanical advantage is. Mechanical advantage has no units because it's not a measure of anything except how many times more is that machine allowing me to do work, to lift. Now, I used a bad word there because I said work, and the work is the same, okay? So if I'm lifting 30 pounds and I have to lift it, oh, excuse me, I'm taking that back, clear screen. If I'm lifting 90 pounds, that's my force, times 1 foot, that's my distance. That means my work is 90 foot-pounds. Foot-pounds is actually a unit of work, but we don't use that in physics. We'll be using joules because we'll be using newtons and meters here. But if that's the same as pushing with a 30-pound force up a 3-foot ramp, right? Again, still 90 foot-pounds of work. So the work is the same. The input work and the output work are the same. What changes is the amount I have to push or the force. Okay. Efficiency, so we have what is known as ideal mechanical advantage and actual mechanical advantage. So you can calculate what the mechanical advantage should be, but in reality, as we know, no systems are completely closed. Therefore, there's probably friction or something else that's causing that machine to be less than 100% efficient. So efficiency is calculated based on the actual mechanical advantage divided by the ideal mechanical advantage, or work out divided by work in. If the 90 joules or 90 foot-pounds didn't equal 90, let's say it equaled 70, then that would mean that my ramp maybe was bumpy or had some maybe there was friction on the ramp that made it so that it was more difficult for me to push it up, and that's probably going to be the case in reality. So that gives some examples of simple machines and how you use them to calculate. Simple machines are calculating mechanical advantage can always be done using force out divided by force in. But if you don't know that, if you don't know what the force out or the force in is, you can use a different way to calculate the mechanical advantage of each machine. For a lever, for example, you are going to measure the distance between the input lever and the output lever. In other words, I'm pushing down on this side of the seesaw, and this side of the seesaw comes up. So where you are pushing is the input, right? So that depends upon where the fulcrum of your lever actually is. So you measure the length of your input arm and you divide it by the length of your output arm, and the ratio should tell you how much mechanical advantage you have. We did the ramp already. We can actually do the, do they have it written in here? Oh, the length of the ramp divided by the height. Mine was a 3-foot ramp that was 1 foot high. So then my mechanical advantage is 3. With a wheel and axle, which is another type, you take the radius of the wheel divided by the radius of the axle, and that gives you your mechanical advantage. When you are using a block and tackle or a pulley system, you look at the number of supporting wires that you have or the number of supporting cables, and that tells you the mechanical advantage of that particular simple machine. So there's usually 2 ways to determine the mechanical advantage. There is the input force divided by output force, and then there's one that's specific to that simple machine. Okay, and then you guys just have some check-in questions, some practice questions, and a quick check. If you have questions on those, if you want me to work through some practice problems with you, let me know. Otherwise, have a wonderful rest of your day, you guys, and I will talk to you in the next one.